The purpose of this lab is to record a physical object moving at a constant velocity and to create a computer model to predict the motion of that object through Newton's second law of motion. The model in this lab is a small roll of masking tape that is moving or rolling at a constant speed in the leftward direction. The same model was simulated in a computer program called GlowScript, utilizing Newton's second law with the assumption that the velocity is constant, thus a zero net force. Iterative calculations of the object positions over time were done over small time intervals, and such calculations were compared to the actual positions of the model over the time interval. Overall, the main result of the lab was that the computer model predicted most of the object's motion accurately, except for a slight overshoot at the later time interval due to potential sources of error. Before observing the experiment and creating a coded model of our experiment, the fundamental principle behind this needs to be addressed. Our experiment relies on Newton's second law of motion. The reasoning for this is that we are attempting to predict a set of motion given a net force and a velocity, which is the reason why we are using such equations. Based on Newton's second law, we will be iteratively predicting the object's position through the following two equations, the vector equation and the position equation. Because we are observing an object that is moving at a constant speed in the video, the acceleration or the total net force acting on this object will be zero. Thus, the initial velocity and will be used to predict the final velocity and thus the final positions. The calculated final velocity will be used to predict the new positions of the object, which will be again used as the initial velocity for the next iteration of the calculation. The experiment video is represented as here. The model row of masking tape is rolling to the left at a constant speed, and this rolling model was chosen as it best represents an object that can move at a constant speed. The system of the experiment is the roll of the masking tape, and the surroundings are the forces that are acting on the object that create a net force. The positions at different times were modeled through the tracker program, which set an axis coordinate system to track the positions over a set time interval of 0.33 seconds, as shown in this time below, and 0.33 seconds were the frame rate of this video. To ensure that the model was at a constant speed, the video was cut to when the object started moving until it was right before it exited the frame. By giving tracker the radius of the objects, as shown in this blue line, it was able to track down the positions at various times as reflected in this table. Through the values on the table, the object's initial conditions were found to be that the initial position of the ball was identified to be negative 0.0027, and the initial velocity calculated through the first two time iterations was 1.15 in the x direction. A simulation of the object was created through this code, which parameters were defined to match the experiments. First, the mass of the object was defined to be 10 grams, and because the net force is zero, the mass was not actually a variable that played a role in this calculation. The initial conditions, as found in this previous tracker program, were set to be here. The position was negative 0.00247, and the initial velocity was 1.15 in the x direction. The initial time was set to be 0, and we used small time iterations for accurate predictions. And a while loop was set to run until the final frame time, which is 0.233 seconds, to continue the calculations below until the object reached its final time. Here, the zero net force is established through the zero vector, and here Newton's second law was also used to update the velocity vector after a time interval delta t. The position was also updated according to the velocity calculated above. Then the program progressed through another time interval with these updated velocity and position values. This was plotted and recorded in the chart and was repeated in the while loop. The output of the code was represented through this chart and table. The table has the various time positions and the predicted positions of the object. So the positions calculated and the positions of the actual experiment were put into an Excel sheet and a graph to compare the accuracy of the model. This graph represents the two predictions and the experimentals. So overall, the model had an accurate prediction of the model of the object as the general trend line for both overlap for the time interval. This shows that at a constant velocity, the motion mostly depends on initial velocity and time, and thus the net force is zero, making the model be able to be accurate in predicting the object's positions. There was a slight overshoot at the prediction at a later time interval, and this could be a source of error in the force of gravity, which was not incorporated in the motion prediction calculation, which could have slowed down the object at a later time frame. Another possible source of error was that when the object was first rolled, there could have been an acceleration from the point of rest to the object in motion, which could have altered the assumption that there was a constant velocity. What if? If the axles of the experiment were set to be opposite of what it was, the positions of the experiment would have been different, and the sign of the initial positions would have been different as well. But overall, the calculations would not be significantly impacted, as only the values would be changed and calculations would be seen. Because our experiment had a constant velocity, our net force was 0. While it would be possible to calculate the net force given the pushes and pull vectors on the object, it would not be possible to determine the exact forces that added together to give a 0 net force on this object. Thank you for your time in watching this video.